Asymmetric Flow Models, or AsymFlow, by Stanford researchers Hansheng Chen, Jan Ackerman, Minseo Kim, Gordon Vettstein, and Leonidas Gibas. We are jumping right into the core insights for the short-form edit.
Right, so modern diffusion transformers, or DITs, they scale incredibly well in compressed latent spaces, but they severely struggle with generating fine, uncompressed pixel-level detail.
Yeah, and moving these architectures directly to raw pixel space causes this massive velocity prediction bottleneck. Predicting high-dimensional noise just absolutely overwhelms a plane transformer's internal attention mechanisms.
Exactly. So AsymFlow solves this bottleneck by introducing a rank asymmetric parameterization. Basically, it keeps the data prediction full-dimensional while mathematically squashing the noise prediction into this low-rank subspace.
Which allows standard DITs to operate efficiently in raw pixel space, right? Without needing any structural hacks like skip connections.
Right. And more importantly, AsymFlow gives us a mathematically exact way to lift massive pre-trained latent models like FLUX 0.2 Klein 9b straight into pixel space generators. You literally don't have to change a single transformer block.
And the result, a new state-of-the-art 1.57 FID score on ImageNet 256 by 256, and text-to-image models that just obliterate their latent base models in raw visual realism.
Yeah, you get the computational efficiency of latent models, but combined with the crispness of raw pixels.
Awesome. So that covers the core takeaways for the short edit. But to really understand how the Stanford team pulled off this math, we need to take a step back and look at why the AI field retreated to latent space in the first place, you know?
Yeah, I mean, for years, operating in a compressed latent space wasn't just a stylistic choice. It was an absolute structural necessity. Transformers just couldn't handle raw pixels efficiently.
And to get why, we really need to look at the fundamental math of standard flow matching, right?
Exactly. So the neural network is trying to predict a velocity target, which we'll call it. And the equation there is pretty simple. It's u equals epsilon minus x0.
Right, so epsilon is the high-dimensional Gaussian noise, and x0 is the clean data.
Yeah, so the velocity u is simply the vector pointing from the noise to the final image.
Just to visualize it, epsilon is pure static, and x0 is the pristine high-definition photograph.
Exactly, yeah. And to accurately predict that velocity target, the network has to actually extract that static, the epsilon, from its input and carry it through all of its internal attention layers to the output.
Which in latent space isn't a huge deal because the dimension is heavily compressed, right? Like by a factor of 8 or 16.
Right. The amount of noise the network has to track is relatively small. But in a high-dimensional pixel space, this massive uncorrelated noise vector has to go somewhere.
And because modern diffusion transformers, or DITs, are literally just plain sequences of attention blocks, they don't have the bypasses that older architectures had.
Yeah, older architectures, like UNets, they relied super heavily on skip connections. You can think of skip connections as a highway bypass for the high-frequency noise.
Oh, so the static takes the bypass straight to the output, and the main network just focuses on the image structure?
Exactly. But modern DITs, because they're designed for massive scalability, they just abandon those skip connections completely. Everything has to go through the main highway.
Which means you're forcing a plane transformer to process 100% of this raw, high-dimensional pixel noise.
And it completely clogs the attention matrices. The network basically spends all its capacity tracking random static instead of learning the actual structural relationships of the image.
It's like trying to listen to a complex symphony, but someone is blasting white noise through the exact same speaker. The system just gets overwhelmed.
Yeah, that's a perfect analogy.
But wait, if tracking that static is breaking the network, why not just predict the clean image and completely ignore the noise? Because that's what models like GT attempt, right? With x0 prediction.
Right, and the theory there makes total sense. Just ask the network to output the clean data and bypass the noise regression entirely. But the failure point is completely mathematical during the generation process.
How so?
Well, if the network only predicts x0, eventually you have to convert that prediction back into a velocity to update the image step by step, through the ordinary differential equation, or ODE.
Right, the ODE being the mathematical path the model takes to slowly denoise the image.
Yeah. And to convert x0 back to velocity, the equation requires you to divide by sigma t.
Sigma t is the specific noise level at that exact time step, right?
Correct. So as the image gets cleaner toward the end of generation, sigma drops practically to 0. Mathematically, dividing your network's prediction by a near zero number is just catastrophic.
Oh, because it's highly numerically ill-conditioned.
Exactly. If the neural network is off by even a microscopic fraction of a decimal point, dividing by a tiny sigma t blows that tiny error up into a massive visual artifact. It just destroys the final sample quality.
So both extremes fail. You force the network to predict all the noise, and it pollutes the transformer. But you predict zero noise, and the math breaks down at the end of the path.
Exactly. You need a way to predict just enough noise to keep the math stable, but not so much that it overloads the attention layers.
And that's where AsymFlow comes in, the optimal middle ground. The Stanford team introduced this new target equation, U sub A equals P epsilon minus X0.
Yeah, U sub A being the asymmetric velocity. The critical addition there is P.
Right, so walk us through what P actually does to the noise.
So P is an orthogonal projector onto a low-rank subspace. Basically, instead of forcing the network to predict the entire high-dimensional noise vector, the network only predicts the noise after it's been squashed through P.
Oh, I see. But the data term, the clean image X0, that remains completely full rank and high definition.
Exactly. So the parameterization is rank asymmetric. The model is predicting this highly compressed version of the static, but a fully uncompressed version of the photograph.
It's predicting the low-res static and the high-res photo.
Yeah, and the authors call this the orthogonal component view. The math behaves exactly like standard U prediction inside that small low-rank subspace, which gives you stability.
But in the orthogonal complement, meaning the rest of the massive high-dimensional space, it behaves exactly like X0 prediction. So the network is saved from processing all that useless noise.
Right, exactly.
But wait, I need to clarify something on the mechanics here. If the network is intentionally ignoring the vast majority of the high-frequency noise during training, how does it properly step backward through the diffusion process when it's actually generating an image? Doesn't it need the full picture of the noise to denoise accurately?
It does, yeah, and that's actually where the elegance of this formulation really shines. You can analytically recover the exact full rank velocity from the asymmetric prediction during the sampling phase.
Wait, analytically? Like perfectly?
Yes, because you have the low-rank noise projection and the full-rank data prediction. The exact relationship between X0, the current noisy image, and the velocity is mathematically locked. The model isn't actually losing information.
Oh, it's just reorganizing how the target is presented during training.
Exactly. The standard flow matching loss function and the actual sampling ODE remain entirely unchanged.
Wow, so it's mathematically a free lunch. You don't alter the transformer architecture, you don't change the sampling algorithm, you just alter the target the network is aiming for.
Yep, it's incredibly elegant.
So to make this work practically, how do they actually determine what P should be? Like, how do they find the optimal low-rank subspace?
Right, so they apply principal component analysis, or PCA, independently within each local image patch. PCA is a statistical technique that basically finds the most important directions of variance in a data set.
Okay, so looking at a patch of an image.
Yeah, a standard 16 by 16 pixel patch with 3 color channels contains 768 dimensions. The researchers found that compressing those 768 dimensions down to a patch rank of just R equals 8 was the absolute sweet spot.
Wait, really? Out of 768 dimensions, they only need a rank of 8? That's retaining like roughly 1% of the dimensional structure.
I know, it sounds crazy, but it works because local image patches are highly redundant. A 16 by 16 square pixels is usually just, a smooth color gradient, a flat texture, or a simple edge.
Oh, right. You definitely don't need 768 dimensions of noise to represent a flat blue sky.
Exactly. So by keeping only a rank of 8, they capture the essential structural noise required for mathematical stability, but they just discard all the high-frequency garbage that clogs the transformer.
And the results back this up. When tested against pure X0 prediction on ImageNet, keeping that tiny rank 8 noise structure dramatically lowered the fresh-8 inception distance, the FID, from 2.68 down to 2.34.
Which is massive. A lower FID means the generated images are statistically much closer to real photographs.
Okay, so we've mathematically proven we can clean up the static using this rank 8 projection on a fresh model. But nobody wants to throw away millions of dollars of compute to train a new model from scratch.
Definitely not.
The real question for anyone listening is, can we retrofit this exact math onto existing massive latent models like FLUX.2?
And this is honestly the most practical application in the whole paper. AsymFlow provides a mathematically sound route to fine-tune a pre-trained latent flow model directly into a pixel space model.
So how does the bridge between a compressed latent token and an uncompressed raw pixel actually work, like mechanically?
They build a patchwise linear lift from the latent space to the pixel space using a technique called Procrustes alignment.
Procrustes alignment.
Yeah, in linear algebra, it's basically about finding the optimal orthogonal transformation to map one set of points onto another. They create this transformation matrix where the columns are orthonormal. And this matrix takes the highly compressed latent tokens, mathematically rotates them, and maps them directly onto the low-rank pixel subspace we were just talking about.
To visualize this, it's almost like fitting a shadow to an object. You take the compressed, lower-dimensional latent representation, which is the shadow, and you mathematically align it until it perfectly overlaps with the structure of the full-dimensional pixel object. The overall shape is preserved.
Exactly, and the math backing that up is super rigorous. In Theorem 1 of the paper, they prove a concept called trajectory coupling. Because the input and output identities of this mathematical lift are exact, the generation path, the ODE, is completely preserved.
Wait, so if you apply this Procrustes matrix to the FLUX model, and you immediately sample an image before doing a single step of fine-tuning,
It perfectly generates low-rank pixels. The high-level semantics, the spatial composition, the objects in the scene, they match the original latent model exactly.
that is wild. But wait, I have to push back here. Procrustes alignment just matches directions, right? What about the actual scale of the pixels versus the latent tokens? Latent tokens and raw pixels have fundamentally different variances.
Yeah, that is a massive hurdle, actually. The scale difference is huge. A pre-trained model's weights are meticulously tuned to expect a specific signal-to-noise ratio at every time step.
Right, the model expects a certain magnitude of noise at step 50, for example.
Exactly. If you just linearly map latent tokens to pixels, and you inadvertently scale the values up by, say, a factor of 8 without telling the model, the signal-to-noise ratio completely changes.
Oh, so the model looks at the magnitude of the noise and thinks it's at step 80 instead of step 50.
Yes, and that causes it to denoise at the completely wrong rate. It ruins the image.
So how is the scale corrected to prevent that drift?
They introduce a scalar calibration factor, denoted as ADDIES. This factor explicitly adjusts the input, the output, and the internal time step routing simultaneously. It basically scales the pixel space variance to match the exact signal-to-noise ratio the pre-trained latent model expects at every step of the ODE.
Okay, so with the Procrustes alignment mapping the directions and the scalar calibration fixing the magnitude, the massive latent model is now successfully living in a low-rank pixel space. It understands the composition.
Right.
The only task left for fine-tuning is to just teach the model how to generate the missing high-frequency, full-rank pixel details. You know, the sharp, photorealistic textures.
Exactly. And training that high-frequency detail efficiently requires some specific loss engineering.
Yeah.
They utilize a variance-reduced fine-tuning loss, or LVR. Because the model already knows how to generate the low-rank structure, the training target isn't the entire image anymore.
It's just the delta, right? The gap between the low-rank pixels and the true full-rank pixels.
Yep.
Yeah.
And to keep the training stable, they apply an adaptive weighting parameter, lambda, which actively minimizes the gradient norm. This drastically reduces the variance of the target, allowing the network to focus purely on learning those high-resolution textures without unlearning the core image composition.
So the network is literally just filling in the gaps. But we mentioned earlier that the end of the generation process, when the noise level sigma is near zero, is highly volatile. Does this variance reduction actually hold up at the very end of the diffusion path?
Well, the variance reduction relies on a mathematical approximation. And that approximation assumes that the variational autoencoder, the VAE used to create the original latent space, is perfectly linear.
And VAEs, by definition, rely on nonlinear activation functions.
Exactly. Because of the nonlinearity in the VAE's decoder layers, the space itself is actually slightly warped. Flow matching assumes the model is walking a perfect straight line from noise to data.
But near the very end of the trajectory, as time step tup approaches zero, that nonlinear warping causes the straight line approximation to fail.
Right, the tangents just don't match up, and this mismatch introduces excessive high-frequency artifacts. The textures come out looking super gritty or like deep-fried.
So if the math just totally breaks down at the pixel level because of the VAE, how do they fix the textures?
They actually abandon pixel-level math entirely at those specific low noise levels, and they switch to perceptual correction. They swap out the variance-reduced loss for an LPIPS loss.
LPIPS being learned perceptual image patch similarity.
Right. Instead of calculating the raw mathematical difference between pixels, LPIPS passes the generated image and the target image through a pre-trained vision network, typically a VGG network.
Okay, so it compares the internal feature activations to determine if the two images actually look similar to human eyes.
Yes. By optimizing for human perception at the very end of the ODE, they completely bypass the mathematical grit caused by the nonlinear VAE, and it recovers these natural photorealistic textures.
That is so clever. So we've unpacked the orthogonal projectors, the Procrustes alignment, the scalar calibration, and the perceptual loss. For the ML engineers listening, the ultimate test is the generation quality. Give us the numbers.
The quantitative benchmarks are pretty definitive. On ImageNet 256 by 256, utilizing a GT816 network architecture, AsymFlow achieves a 1.57 FID score when combined with RPA loss.
RPA stands for representation alignment, right? Which just helps the network align its internal features with a pre-trained vision model for better global structure.
Right, and a 1.57 FID just completely outperforms prior raw pixel models.
But the text-to-image application is where this math truly proves its worth, honestly. They applied this exact lifting technique to the 9 billion parameter FLUX.2 Klein latent model, creating AsymFLUX.2 Klein.
Yeah, and when evaluated, the pixel space AsymLVLUX actually beat its own latent-based model across major industry benchmarks. It scored higher on HPSv3, DPG Bench, and Genival.
Which is huge because those benchmarks evaluate critical capabilities. Genival tests fine-grained spatial reasoning and composition. DPG Bench measures strict prompt adherence. And HPSv3 evaluates overall human preference and visual quality.
Yeah, taking a highly optimized, state-of-the-art foundational model and measurably improving its visual fidelity and prompt adherence simply by mathematically shifting the space it operates in. That is a massive achievement.
And the qualitative examples in the paper really illustrate why it scores so high on visual preference. There's this highly realistic generation of an intense boxing match.
Oh yeah, that one is striking.
To demonstrate how crisp text rendering becomes an uncompressed pixel space, the prompt actually requires one fighter's headband to read pixel and the other fighter's headband to read latent.
And the text is rendered flawlessly. Plus, the sweat flying off their faces upon impact is just razor sharp.
Yeah, because the visual richness of pixel space generation is fundamentally different from a latent baseline, right? A latent decoder, by its very nature, acts as a slight low-pass filter.
Exactly. It washes out fine, high-frequency details. Standard latent models really struggle with microtextures like individual pores or fabric weaves or particulate matter. The AsymFlow pixel versions just remove that filter entirely.
There's another example in the paper that shows a hyper-detailed texture of men exploring a dystopian landscape in yellow hazmat suits. In the latent baseline, the suits look a bit plasticky and smooth.
Yeah, but in the AsymFlow generation, you can clearly see the grit, the scorch marks on the terrain, and the heavy woven texture of the protective fabric. It's incredible.
There's also this prompt for a giant octopus crushing a car in a town at night, explicitly styled like a 1980s Jeff Wall photograph. The specular highlights on the wet asphalt and the individual suction cups on the tentacles, they're rendered with absolute photographic precision.
For years, the industry basically accepted the slight blurriness of latent decoders as the necessary cost of scaling up parameters. AsymFlow mathematically proves that this trade-off is just no longer required.
We can leverage the computational efficiency and semantic understanding of latent models while achieving the uncompressed crispness of raw pixel generation.
Exactly.
But this shift toward uncompressed photorealism does introduce broader industry implications, specifically regarding safety, right?
Yeah, the authors dedicate a portion of their impact statement to dual use concerns. When you combine uncompressed, flawless photorealism with the ability to generate perfect text directly onto the image, like the boxing headbands, you significantly lower the barrier for creating convincing disinformation and deepfakes.
Because as models move away from latent artifacts and toward true raw pixel fidelity, robust digital watermarking and pre-generation safety filters become completely non-negotiable. The forensic markers that used to distinguish AI images are disappearing.
They really are. The responsibility scales directly with the capability here.
Definitely. I want to leave you with a broader implication to ponder. Building on all of this, AsymFlow provides a mathematically rigorous way to map a lower dimensional latent representation directly back into high dimensional raw data without altering the underlying transformer architecture.
Right.
If Procrustes alignment and trajectory coupling hold across different modalities, what does this mean for other fields of machine learning? Could we use this exact latent-to-raw LIFTA technique to adapt large language models to generate raw audio waveforms directly?
Oh, wow. Yeah.
Could we map latent representations straight to raw genomic sequences,
Yeah.
completely bypassing discrete tokenizers and the bottlenecks they create?
I mean, if the mathematical bridge holds, the tokenization bottleneck that limits so many multimodal applications could be permanently bypassed. It's huge.
It really is. Thank you for joining us for this deep dive on AI paper podcasts. We'll catch you on the next one.